We'll start from here. So number one, there is a refracting layer beneath the surface of the Earth that can be estimated using techniques developed by seismologists. One technique is based on the time required for vibrations to travel from a distant explosion to a receiving point. The depth measure, m, is the sum of the true depth, d, and the random measurement, e, random measurement error, e, which leads to the formula m equals d plus e. The measurement error, e, is assumed to be normally distributed with a mean of 0 feet and a standard deviation of 1.7 feet. All right, so that's really the important part they're giving us there is mean of 0, standard deviation of 1.7. All right. If the true depth of a certain point is 2 feet, what is the probability that the depth measurement will be negative? All right, so that 2 feet depth is being added to the error. All right, so the true depth 2 feet doesn't have a standard deviation. That is just the true depth. So this gives us a new normal distribution of 2, 1.7. So 2 is our mean, 1.7 is our standard deviation. So we'll have this normal distribution centered at 2. And then we're asked, what is the probability that the depth measurement will be negative? All right, well, negative would be below 0. So we want to know what's the probability that we're down here. So to find that area, that's just normal CDF. Our lower bound would be something really small. Our upper bound would be the 0. Our mean is the 2, and our standard deviation is the 1.7. So now we just pull out our calculator wherever it may be, turn it on, back to life. Second distribution, oops, that's right. I'm so used to going to binomial in the other class. Normal CDF, our lower bound, yeah, that'll work. That's something very far negative. 0, a mean of 2, standard deviation of 1.7, and voila. And we get 0.119 and some change. Somebody else showed up, Anthony's here. Sorry, I gotta make sure to add people here for attendance purposes. So there's our answer to the first one, 0.119. All right, next, part B. So this relies on your answer for part A. So here's the catch. If you did part A completely wrong, whatever answer you got from part A is what you're using for part B, and you'll still get absolutely full credit for part B, I promise. All right, so suppose 4 independent depth measurements are taken at a point where the true depth is 2. So this is still what's actually happening, all this stuff up here. What is the probability that at least one of the measurements will be negative? So the probability that at least one will be negative is 1 minus the probability that none are negative. All right. So that's how we always did the at least problems. We figured what was the complement. So none, at least one negative and none negative should add up to 1. So 1 minus the none negative should equal the at least one negative, which is what we want. So none negative, we would mean that probability that each one is not negative. So each one not negative happening 4 times because we're doing this 4 times. All right, so the probability that we were negative was this. So the probability of not negative is 1 minus that. 1 minus 0.119 to the 4th. Or in other words, it's this side over here is what we're really asking about. And that would be, I don't know what that is off the top of my head, but that is something we could just type into the calculator from here. So let's see. 1 minus parentheses, 1 minus 0.119 close parentheses, raised to the 4th. And we get 0.3975 and so on. So 0.397, 0.398, whatever, but something along about 40% would probably get you full credit here. All right, so how is this scored? So the first one, we had to say that it was somehow normal. If you wrote normal CDF, that covers that. You had to recognize the mean and the standard deviation. If you wrote out the normal CDF and labeled your parts, that also covers that. And you needed to calculate the correct probability, which was the 0.119. You could put 0.12, that was perfectly fine. 0.11, also okay. If you drew the picture and just labeled it just like this, that in itself is full credit. Right? You don't have to show the actual calculations if you have the picture. All right, so that's the first part. And if you just did two of those things, like if you said it was normal and you calculated a correct probability based on your situation, whatever you had the situation to be, that also gets you a P. So if you didn't know the mean or standard deviation correctly, but you still calculated a probability correctly based on what you were doing, that should still get you a P here. All right, for the next one, yep, here's our at least one minus probability of none, and we get the 0.39 something. They got 3995. Actually, this is when I did this with a few more decimal places. That's what we get. So for an E, they calculated the correct probability or calculated the correct probability based on a wrong answer from A. All right, so if you got to this answer or something close to 0.39 or 0.40, that gets you full credit, no matter what you did. As long as you showed a little bit of work here, that's fine. Like really, this was the big line. That's how you get your answer right there. So if you had that, that's probably great. That gets you straight to that answer. All right. If identified it with binomial with n equals 4, p equals the probability of that, we got the wrong probability, that gets you a p. I don't know if anybody tried to do this as a binomial, but it would also get you close. All right, the next part, skip the part. Part C, what's the probability that the mean of four independent measurements, the mean of them taken at the point where the true depth is 2 will be negative? All right, so now when we're taking these four and finding the mean, that makes this a sampling distribution. So first we have to find the mean of the sampling distribution. It's still going to be 2. That's not going to change. But we need to also find the standard deviation of the sampling distribution, which was the standard deviation before divided by the square root of our sample size. So our standard deviation of before was 1.7. Our sample size here is going to be 4. I know we're not used to doing it with something this small, but it still works. So if we do 1.7 divided by square root of 4, we get 0.85, I believe, half of 1.7. All right, and now we're doing basically the exact same thing we were doing before. We want to know the probability that we are negative. All right, so again, it's going to be normal. All right, because our population was normal, so that means the sampling distribution also normal. I don't know if you need to note this. Actually, I don't think you need to note that, but if you did, cool. The lower bound again is going to be something very small. The upper bound would be the 0 because we're asking about negative. The mean is still going to be 2. The standard deviation, this is what's going to be different, the 0.85. And our probability should be very different than the last time. Second distribution, normal CDF. Got to get my participant list out of the way here. There we go. So we're just changing the standard deviation to half of what it was before. So 0.85. And what do we get? 0.0093. There's our answer. All right, and how did we score that? Well, really all you needed to do was write out the normal CDF stuff with the parts labeled, and that got you full credit. But if you noted that it was normal somehow, whether you wrote normal CDF or normal sampling distribution because it's a normal population, that's fine. If you got your mean and standard deviation correct, like if we wrote mean and standard deviation, here's the 0.85 right there, or actually worked it out, that would get us the point for that one, and calculates the correct probability. There's the correct probability. You could have also drawn the normal graph and labeled the sections again, but now it would have been like a much narrower graph and hopefully maybe a smaller section out here like that. All right, so that was the first problem. All right, you could also do this by, summing them up to say we had four different independent observations. So 4 times the 2 should give us a mean of 8 if we're adding them together. But then we'd have to add together 1.7 squared as a standard deviation 4 times and then take the square root. Remember, we used the Pythagorean theorem to combine standard deviations, and that would get us 3.4. So if we treated the mean as 8 and the standard deviation at 3.4 and still asked what's the probability of being below 0, we'd actually get the exact same answer. It's neat how that works out, but it's not really the easy way to do this problem. It's much easier to do this as a sampling distribution. All right, so there's our scoring for that one. It's a little more different than normal. The EPI is usually a 2, but this one, for whatever reason, it was a 1. Otherwise, pretty much the same. All right, the next one. There is going to be one like this on your AP exam this year. Right? It will be there, right? Because it says that experiment design is going to be one of the free response questions. This is like the basic experiment design question. All right. They like to ask you to list the treatments, and then they like to ask you how to assign the treatments. That's always involved in the experiment design ones. So a marine biologist is studying the effect of size enhancing vitamins and different salinity or salt levels in water on the growth of shrimps. The marine biologist has ordered a large shipment of juvenile white shrimps from a supply store for use in the study. The experiment is to be conducted in a laboratory where 10 white shrimps are placed randomly into each of 12 similar tanks. In a controlled environment, the marine biologist is planning to use 3 different size enhancing vitamins A, B, and C, and 2 different salinity levels, low and high. List the treatments. List them that the marine biologist plans to use in the experiment. We don't have to do anything with them, just list them. So we've got 2 salinity levels and 3 vitamin levels. So we've got A low, A high. We've got B low, we've got B high. We've got C low, and we've got C high. CeeLo green. All right, that's it. That's all they were asking for there. If you want to put them in parentheses or whatever, you want to make a chart or a table or whatever, that's fine, but that's what they wanted. They wanted the 6 treatments somewhere listed. All right, part B. Using the treatments listed in part A, describe a completely randomized design that will allow the biologist to compare the shrimp's growth after 4 weeks. All right, so now we have to come up with this completely randomized design. All right, well, we've got 6 treatments and we've got 12 similar tanks. And each of those tanks has 10 shrimps in it. Is it shrimp or shrimps? I guess it's shrimps. Yeah, who knows? Sure, there's some way we could look this up. All right, so 6 treatments, 12 tanks. That should tell us right away that we're going to have 2 of each treatment. All right, so we're going to have 2 tanks of each of those treatments. All right, so now what we should do is we should, so now that we have an idea of what's happening here, or how many of each treatment we're going to do, we're going to write 2 of each treatment onto pieces of paper. Put the papers in a hat, mix them, and walk to each tank. Select a treatment from the hat for each tank without replacement. And let's see, completely randomized design that allow biologists to compare the shrimp's growth after 4 weeks. So we probably want to say, weigh the shrimps before starting and after 4 weeks. Compare after minus before. All right, I don't know if we needed all that or not, but that would be my completely randomized design. That's the entire experiment right there. All right, I think they just wanted the randomized assignment part, but there's everything. So I put the weigh thing on there just in case. All right, so here are our 6 treatments. So here they are right there, or they put them in a table here. This is how they did it. So if you have all 6 treatments listed, that's an E. That's all you have to do. If you just listed the factors, like the factors are vitamin A, B, and C, and high and low salinity, that got you a P. That's not treatments. Those are factors. All right, so like one factor would be the vitamins or the nutrients. One factor would be the salinity level, low or high. All right, but we wanted the treatments that's putting it all together, what's actually going to be assigned to stuff. All right, the next thing, so for the assigning them, so we stated that 2 tanks were getting each treatment. So we said that right away. And some sort of randomized assignment procedure was stated and understandable. So that would include the hats. I think this one, they numbered the tanks 1 through 12 and pulled them out of the hat and just first one out is number 1, second one out is tank number 2, third one out is tank number 3, and so on. All right, it looks like they said 3 weeks. I don't remember if it was 3 weeks or 4 weeks. I know I had this as a different problem and I've changed it a couple of times, the wording, so people couldn't Google it as easily. All right, so just any sort of random assignment, use the hat. Please, please, please use the hat. Do not try and use a random number generator. Too many things that come up. All right, the other 2 things we asked about here are advantages and disadvantage. So I think you had a question like this on one of your tests. So give one statistical advantage of having only the white shrimp. Explain why this is an advantage. All right, so having only one type of shrimp, there should be an R in there, eliminates some confounding variables from other types of shrimp. All right, now explain why this is an advantage. So now this is what's happening. We're eliminating confounding variables, but we have to explain why this is an advantage. And the reason why this is an advantage is because this will lead to decreased variability. All right, eliminate confounding variables, which leads to decreased variability. And I guess we could, what else could we say? We'd better know what works for this type of shrimp, I guess the white ones. All right. All right, so we're trying to explain what this advantage does for us besides just saying that it eliminates confounding variables. It also decreases variability and it gives us better results for the shrimp that we know about. All right, give one statistical disadvantage to having only white shrimp in the experiment. Explain why this is a disadvantage. All right, so the disadvantage here is our results will only apply to white shrimp. And not to other types of shrimp. All right, so, and this is because we only used white shrimp in our experiment. All right. I think we did this with roses in the beginning of the year. I don't remember exactly the question. Hopefully you've done this before. So the statistical advantage that we're looking for was reduced variability is specifically identified. Right, that's the one they wanted. All right, so if you just said eliminated confounding variable, that's not enough. An appropriate explanation that relates reduced variability to increasing the likelihood of determining differences among treatments is provided. What does that even mean? Here's variability to increasing the likelihood of determining differences among treatments is provided. Yeah, I don't think we did that. Better know what works for white shrimp. Maybe that's what we were talking about there. That's what they're going for with that one. Yeah, they were very nitpicky on this. They tried to make this one really hard to get an E. Right. The second one, though, the disadvantage that it only works for the white shrimp, and other species may respond differently to different treatments or differently to treatments. So we need something about that it only works for the white shrimp and it will not be able to determine the other types of shrimp. All right. So again, if you had one of these 2 things, which probably you had part 1, that's definitely a P there. All right, so there were 4 parts to this one. Each E is 1 point, each P is half a point, each I is 0 points. All right, and that is it for that. So let's move now over to the multiple choice. Let's see how good it hadn't cleared on me yet. Sometimes it likes to kick me out if I'm inactive for too long. All right, so for the most part, you guys did pretty well here. I don't know if it was you guys or other people, because I didn't check to see who did this. But most of the questions we did pretty well. There's 2 of them in a row here that are basically the exact same question. And we didn't get it right either time. So, you know, I mean, that makes sense. If you miss it once, you're probably going to miss it the second time. All right, so let's look at those 2 here to start. So a researcher is studying the sleep habits of teens will select a simple random sample of N teens from a population to survey. The researcher will construct a T interval to estimate the mean number of hours of sleep that teens in the population get each night. Which of the following is true about the T distribution as the value of N decreases from 40 to 20? All right, well, with T distributions, decreasing the size of N will not affect the middle, right? Just like it won't for sampling distributions or Z distributions. So the center increases or decreases is wrong. The center remains constant. It's not going to change. All right, what does change is when N is greater, it approaches more and more of a nice normal distribution. So this is N greater. All right, if N is smaller, it's kind of more smoothed out. It's kind of more like that. All right, and this is for T distributions. All right, it's kind of like saying your standard deviation gets smaller and smaller as N gets bigger, which is true for sampling distributions as well, guys. So it works kind of like that. All right, so which one of these, let's see, the area, the tails of the distribution remains constant. No, like the tails would be like if we took a particular spot and said, okay, beyond here is your tail, the outsides. It's not going to remain constant. It's definitely going to change. The area of the tails decreases. Well, as we go from 40 to 20, this would be the 40. And then this one here would be the 20. Now it looks like this area is a lot less than this whole area over here. So it's not decreasing. It's actually going to increase. All right, so that's that one. And the next question was almost the exact same question. All right, so what happens to the distribution as the degrees of freedom increase? Well, the degrees of freedom works just like N. Remember, your degrees of freedom is just 1 less than N when we're working with T distributions. All right, so what changes as the degrees of freedom increases? Well, this is the same thing. Degrees of freedom. It's just N minus 1. All right, so the center remains constant. Center remains constant. One of those 2 increases. No, center doesn't change. And let's see, the area of the tail increases, the area of the tail decreases. All right, so now we're going backwards. We're going from this one to this one. So now the area of the tail is getting smaller. So the area, so the area is decreasing for this one. That's why I have my drink handy. All right. And let's see. Here, the drawings. Is there another one here? Yeah, maybe the one that had 9. There's 2 of them that had 9. All right, let's look at one of those. So this is choosing the correct procedure. Most appropriate inference procedure to analyze the results. So is it 1 sample, match paired, or 2 sample, basically, is what we're asking here. So let's see, what are the keywords here? Study of certain adult reading program. Researchers will select a random sample. So it looks like we have 1 sample so far of adults who are eligible for the program. The selected adults will be given a pre-test before the beginning of the program and a post-test after completing the program. The difference in the number of correct answers on the pre-test and the number of correct answers on the post-test will be recorded for each adult in the sample. Select which of the following is the most appropriate procedure. All right, so it's the same adults doing both tests. All right, so since it's the same person doing 2 things, then that is going to be match paired. They're matched with themselves. All Right, so each person matches with themselves, and it's always, when we're doing the match pairs, it's always T, and it's always for mean difference. All right, so that's the test we want to use for that one, for sure. All right, and what was the one other one there? We had 9. There it is. Or maybe there were 2 other ones that had 9. I think we did better on the other section, by the way. To estimate the average cost of flowers for summer weddings in a certain region, which I'm going to do next summer, a journal selected a random sample of 15 summer weddings that had been held in the state. A graph of the sample data shows approximately symmetric distribution with no outliers. So that's our normal condition met right there. The sample mean and standard deviation were that and that, respectively. Journalists will create a 95% confidence interval estimate for the population mean. Have all conditions for inference been met? Let's see. No, the 15 weddings in the sample were not selected at random. Well, did it say selected at random? Yes, they were. No, the sample size is not large enough to assume the distribution of the sample means is approximately normal. Well, they don't need that because we're doing the graph here. They looked at the graph. No, because the graphical display. Nope. No, this says 15 is not less than 10% of weddings. It very likely is less than 10% of weddings. So yes, all conditions here have been met. Looks like most of you, that was the most popular answer. All right, but yeah, you don't need a certain sample size if you look at the graph and it's symmetric and no outliers. That's even better than not skewed and no outliers. All right. And there was another one here with 9. I thought, there we go. Spider webs. All right. Researchers studying the sticky droplets found on the spider webs will measure the widths of a random sample of droplets from the sample. The researchers will construct a 95% confidence interval to estimate the mean width of all such droplets. Which of the following statements about the 95% confidence interval for the mean is correct? The interval will be narrower if the researcher increases the level of confidence. No, actually, it gets wider when we get more confident because we're guessing more numbers when we're more confident. The interval will be narrower if the researcher increases the sample size. Well, yeah, that's true, because remember the standard deviation is, well, I guess we're not using this. We're not using that. But it's the standard deviation of the sample divided by the square root of n. So if n is bigger, then that means that the standard deviation of the sampling distribution will be smaller, right? Because n's getting bigger down there. So that is true, that's for sure. The interval will be wider if the researcher decreases the level to 90%. No, actually the interval gets smaller when we're guessing less stuff. So it's like this and this would basically be the same answer. So if this one's right, then this one must be right, right? Those would both mean the same thing. The interval will be wider if the researcher increases the sample size of droplets. No, these two are the exact opposite of each other, and for the exact opposite reason. The width of the interval will not be affected if the researcher increase or decrease the number of droplets. Nope, when we change the sample size, we change the width of the interval as well. All right. So let's check on the next section here, part B, which I think we did slightly better on. And I will check attendance again, and that will be that. All right, so there's a 9. Oh, wow, 14 right. Oh, we got these 3 right here for sure. And there's another 9. All right, so let's look at these 3. All right, so let's see. A sociologist is studying the differences in ages between husbands and wives obtained from a sample of 55 married couples. The mean husband age is 38.5 with a standard deviation of 12.6 years. The mean wife age is 36.9 with a standard deviation of 12.4 years. The sociologist calculated the difference between the ages for each couple. The mean difference was 1.6 and the standard deviation is 2.1. A matched paired hypothesis, or matched pairs hypothesis, test will be performed to investigate whether the difference is significant. Which of the following is the standard error for the test statistic of the hypothesis test? All right, so again, the standard error is kind of like our sampling standard deviation. It's the standard deviation of the sample divided by the square root of n when we're working with means. Right? So we're not combining 2 different distributions here. It already says we're doing match paired. So we're taking the difference and then we're just looking at that as like a single sample. So this would be the 2.1 from here divided by the sample size, which is the 55 married couples. And that's how we're getting our answer here. All right. So that's that one. Let's move on over to the next one here that we struggled with. Let's see if it's more of the same stuff here. Interpreting a p-value. We had a lot of these last time with the other ones. All right, so interpreting the p-value. It means if H0 is true, then the probability, or the p-value, is the probability of getting this sample value or more extreme. We probably should have done more of this. I kind of cut it out some this year. It was one of the things that had to get chopped so we had time. But yeah, this is what the p-value actually means. We did look at graphs and we did talk about this just a tiny little bit, but not a ton. So what the p-value is we treat the null hypothesis to be true. Whatever that mean is, we pretend that like, oh, we've got a normal sampling distribution with that as our actual mean, our null hypothesis mean. Pretend that's true. And then we get this sample somewhere out here. And now this probability, or is this above, or actually this one was below, but all right, so we get some sample that's down here. So the p-value is this area. All right, it's the probability of getting that sample value or farther away. In this case, farther away is below. So if the mean typing speed for the workers is 60 words per minute, that's our null hypothesis mean right there. The probability of selecting a sample of 50 workers, which was the sample size that they selected up here, 50 workers, with a mean of that, which is what they had, or less, because that was what our alternative hypothesis, evidence the typing speed of workers is less, there's the or less than 60 words per minute, is that p-value. Right, so that's how we interpret a p-value when we're not just trying to conclude yes or no. Right? Or to reject or to fail to reject. I imagine probably the next couple ones are the same thing here. Yeah, that looks like the same kind of thing here. All right, so which of the following is the correct interpretation of the p-value? So again, if the null hypothesis is true, I don't even know what the null hypothesis, but the probability of observing a sample with mean of 5.11 or less, or that or more, if the true mean of is 5.2 is the p-value. Okay, so this was a two-tailed one, which made this even a little harder. But what happens is we've got this normal distribution with a mean of 5.2. That's our null hypothesis. 5.2 is the mean. All right, and we got a, what do we get, 5.11? Looks like, yeah, sample size of 50, we got 5.11. So down here would be 5.11. But since we're conducting whether there is evidence that the pH is different, so that means our alternative hypothesis is that the mean is not equal to 5.2. So that means we need to take this p-value and double it, or this area here and double it, and that's where we get our p from. So if we say the difference between these two is 0.09, just subtracting, we also go 0.09 up. So this would be 5.29, and we'd add this area, and then these two areas together give us our p-value since it's a two-tailed test. All right, so we want to be less than 5.11 or greater than 5.29. And those two together, the probability of those two extremes is our p-value, given if the null hypothesis is true. All right, that is how we interpret p-values. That's what the p-value actually means. All right, we would probably reject in that case because our p-value was so low. All right, we're back to doing well here. There's another one. All right, so which inference procedure do we want here? So let's see. Occupational safety officer with a large company is conducting a study to investigate back problems in office workers who use a computer for most of the workday. That's me. The study will investigate the difference in back problems for workers who stand and workers who sit. A group of 6 to 8 volunteers have agreed to participate in the 9-month study. Half of the group is randomly assigned to work while standing. The other half is assigned to work while sitting. the end of the study, the mean number of back problems between the two groups can be calculated. The officer will use the results to estimate the difference in the mean number of back problems between those who work while standing and those who work while sitting. All right, so we're breaking this up. We're not comparing individuals, we're comparing two different groups. So which of the following is appropriate inference procedure? So we're definitely going with two samples because we've broken it up into two samples. All right, we are dealing with means, so it is T. All right, so both of these are intervals. So we could also do a hypothesis test to see if there's a difference. All right, we don't do tests for sample information. We do tests about populations. All right, so if we do intervals or tests, we are concluding about a population, not about a sample. So almost nobody chose this one, so that was good. But it is definitely two samples because we're breaking it up into those two completely separate samples, and we are not matching them together. And I know we had one sample to start, but when we broke them up into two separate groups, that's when we make it two samples. All right, so that one is two samples. Mostly good there, about half and half there. Oh, this is just, do you know the formula or not? And you have formula sheets, by the way. All right, so the rest of them looks like we did okay on. All right, so let's see.